Oftentimes we have long tables with lots of numbers. And once we want to communicate our results more effectively, visualizing results becomes central and very important. And that's what this webinar is all about. We will deal with a few visualization techniques. We will start with a few descriptive visualizations without any statistical background, no regressions. Then we will turn to a linear regression, where we will look at how we can visualize an ordinary least squares regression and the results thereof. And then we'll turn to more complex issues. We have a moderation analysis, which requires a few additional analyses and also a few points to keep in mind when visualizing those results and interpreting the results. And we also look into nonlinear models, such as logistic regressions, which bring their own set of problems. So a lot to cover for today. Let's get started. I have a script prepared for you. Now, if you are not familiar with Stata, then let me briefly highlight what you see here on the screen. On the right, I have my script, which I prepared in advance, and which will also be shared once the recording is finished, and you can download everything and revisit everything. You can take notes, you can walk along, but if anything goes too fast, then no problem, you will have access to everything. On the left, you see my output screen, where all the results will be displayed, all the regression results. And once we come to visualizations, they will pop up in a separate window. We'll come to that later. Everything that is green on the right is code annotation, meaning that is not part of the actual computation, but just my explanations. As you will see, there are lots of explanations so that when you revisit the script later, hopefully everything is self-explanatory. Okay, now, what do we have here? We have a data set that we first of all want to explore. It is a data set that explores women wages of the 1988 National Longitudinal Survey. This is a data set that is available in the Stata library. The advantage is we can all access it directly. It's kind of built in to Stata. Everything that I need to do, first off, is to wipe my memory. That's the first command that I'm executing. You have now two options. You can highlight these lines of codes that you want to run and then click on this run button up here. What I'm going to do is I'm hitting the Control D command on my keyboard, and that will automatically execute those highlighted lines or rows in my script. The set more off command keeps data running when we have a very long code. It doesn't stop. Otherwise, you would have to click to continue the computation. It's a standard setting that I always put on. Now, this data set is a data set that contains information on wages, and you see a few variables here. Let's take a quick look. So we have IDs for the individuals in the data set. We have their age. We have race, we have whether they're married or not. Then we have whether they have been married before. We have the grade, the number of years in school. We have geographic information, the industry they work in, whether they're in a union. We have the wage, the hours worked, the experience they have with tenure, and so on. So it's a typical survey data set that contains individual level information on people that have worked, and in this case, in 1988. The first thing that I'm doing is I'm preparing a few variables that I will need. The first one is the log of wages. Typically, wages tend to be skewed. We have a few people that earn very little, and then we have a few that earn a lot, such as now the boss and the team. And that skewness will also lead to a situation where we have some outliers. And the log kind of takes care of that distribution. As a result, the interpretation of my coefficients related to wage will also be related to a percentage change, which is a common convention in wage research. That's a little bit of background. Now, what I want to do is I want to create a variable that is binary if the job that this person takes is a blue collar or a white collar job. Blue collar would be something like agriculture, manufacturing, so labor intensive work. And then blue collar work would be more cognitive related works, you know, something like a lawyer, a service person. Those jobs would be white collar. That is what I'm doing here. I'm first creating this binary variable based on the occupation that is present in the data set. If we recall, now there was an occupation variable here, which has operatives, craftsmen, sales, other professional, technical, different professions that we see here. And this binary variable then captures whether this occupation falls within the blue color or the white color category. I use that specifically to later have a binary outcome variable for my logistic regression. That's just a preemption. Let's create this, and then we can also look at those variables on the left. We see that we have a few descriptive statistics. First of all, how the variable race is distributed. It's a categorical variable with 3 expressions, white, black, and other. And then for blue color workers versus white color workers, I see also the distribution. 69% of the occupations in the data set are white collar jobs, and then around 30% are blue collar jobs. That's all that I need for now. That's just the 2 variables that I will work with in my regressions. Everything else is already in my data set. I can work with that directly. Part 0. We go to descriptive statistics. The very first thing that I tend to do when I work with data is to look at descriptive statistics. Nothing fancy, just the raw data illustrated. And that helps me to understand the distribution of the variables and the variance. When we look into regressions later, what we are looking for is variables that have a lot of variance. If they don't have a lot of variance, then typically things become very difficult to predict because regressions work with variance. First thing, therefore, is to look at what is the distribution like, what is the variance like. Let's take a look at this first plot. It is a k-density function, which is similar to a histogram really, but smoothened out. It shows me how the values of, in this case, the log of wages is distributed. If I look more closely at the code, I see that we have 2 groups here. We have union is equal to 0, which means that in this case, the person is not part of a union. And then we have the wages of those who are part of a union. That's why this is set to 1. Remember, union is one of the variables in our data set, and it has 2 expressions, whether you are in a union or whether you're not in a union. And this allows me now to see whether the distribution of wages for union workers is different from non-union workers. All right, let's take a look at this code. The two-way command creates that plot, and the k-density is the function that I'm using for this plot. What I see now are 2 nice lines. The blue one is the wages for union members, and the gray dashed line is for non-union members. And what we already see here is that the wages for the union members tend to be slightly higher than for the non-union members. That's a first descriptive result. In terms of the code, what we see at the bottom here is mainly options. For example, how I want the legend to be displayed, which font size, for example, that's the font size, which position on the clock, where that would be positioned. Now it's positioned at 11 o'clock, so that's upper left corner. I also specified the background color to white and the plot region to white. Then I added labels such as for my X title. Now that's the label for my X axis and the Y axis. And I also provided a title for the graph. All of this is optional. You don't have to do it. Stata has a standard form. If you don't specify any of this, then it will work with the default. But those options are typically a nice way to improve the visualization of this graph. And this logic of having a standard command like two-way and then the type of plot you want to use, followed by the option, that's the format we will use for all the figures in our later regressions as well. Same logic always. You have your standard visualization command, then you have a comma, and after the comma, you have all the options for improving and adjusting your visualization. The final thing is I want to export this. You have different ways to export this figure. You can export it as a JPEG, as a TIFF. That's what I chose here. You can use a vector graphic, which can be easily scaled. That's all up to you. The width and height is the size of the image. If you want to have a high resolution image, you just add more pixels to the width and the height, and then you're done. The other thing that I specified here is the directory for saving my graph. If I run this command, then I actually can go to my webinar folder, and now I can open this image, and there we go. I have it ready to export. You can see here there's a slight mishap. So the figure here looks, so the box for the legend is actually now too small. An easy fix for this internal error of Stata, so to say, is to simply add a few empty spaces after a union member, for example. Now, I just wanted to highlight this because that happens quite frequently, these little things. So if you just add a few spaces here, for example, after union member, then it should look fine. Another plot that I want to share is the graph bar. That's another figure that we can use to show a bar chart. In this case, I want to plot again ln wage. If I just use the first part of the code, graph bar ln wage, then that would already result in a figure that is okay. Now it looks not too terrible, but of course that is just with the inbuilt Stata default setting in terms of the colors, in terms of the labels. If I want to beautify this a little bit, I can again add my options. Now the type of labels I want to use, the type of colors I want to use. So let's run this as well. And you see now it looks a lot smoother in terms of the colors. We see again the mean log of hourly wage on the y-axis, and then we split this up by white collar workers and blue collar workers to see if their means in salary is different. And we already see, okay, there seems to be a slight difference in those average wages. That gives us a first indication, maybe that's something we can explore later in our regressions. Again, I'm going to save this to my document folder, and then I can draw on it again. So here, that's my final figure, and that's what I can then also use as an output for my paper, for example. We will come now to our next part, visualizing the direct effect of a continuous predictor. The first step in this part will be to run a regression. The regress command in Stata runs an ordinary least squares regression, meaning that I predict a linear model where the dependent variable is not binary but continuous. In this case, wage is a continuous variable ranging from 0 to infinity probably. And the important part about the dependent variable is that there are few assumptions. Typically, it should be roughly normally distributed. I can check this easily by looking at the k-density plot again. So I just type in my command line k-density followed by ln wage. And what I see is after the log transformation, it has a pretty nice bell shape. So in that case, the OLS regression would be a good fit for this type of dependent variable. My independent variables follow after the dependent variable. So we have hours, age, tenure grade, and whether the person is married. Note that I put an I dot in front of married. That is because when I use the married variable, it's binary. And by putting an I dot in front of it, Stata knows, this is a binary variable. That can be relevant, especially when we look into moderation analyses. Let's run the regression. So in this case, we see that the number of hours worked has a positive direct effect on my outcome, the wages. That would be expected. If I work more, I would probably earn higher wages. Now let's try to visualize this. The first thing that I'm going to do is that I look at the range of hours. How many hours do we have? If I look at summarize, then I see that the minimum is 1 hour worked and the maximum is 80 hours worked per week, a very intense week. The mean is 37. I'm now going to save the minimum value, the 1, and the maximum value, 80, in a local. A local is a temporary memory in Stata, which allows me to store values. Any sort of values can be stored in the local, and it will only be stored for the period of running this specific command. So right now, nothing is stored. And even if I run it now and stop running anything, it will be deleted again. So it's only in a very short-term memory. Afterwards, I use the margins command. The margins command is, technically speaking, the first derivative of the regression function. So if you think of a regression as y equals beta 0 plus beta 1 times x1 plus the error term, then the margins computes the first derivative at specific values of the specified variable. In this case, I want to derive it by the hours worked from the minimum value, that is from 1 hour worked, to the maximum value, that is 80 hours worked, in steps or intervals of 1 hour. All the other variables should be kept at their mean value. That's what the at means option means. Afterwards, I can compute the margins plot. Let's start with the first part. Now I can compute the marginal effects for all the different combinations I have here. For example, 62 here, that's where the hours is set at 62 hours worked, and all the other variables are set at their mean value. And if I go to 62 in my output, that's where I would find the corresponding marginal effects. That's the first column. Then the standard error, that's the second one. Then we have our t and p values, and we have our confidence intervals. So here in this table, number 62 corresponds to the marginal effects that I computed earlier in this long list here, where I can see at which values the margins were set in this case. That's actually all I need to do. To visualize my results, I need to compute the margins so that I have point estimates at different values of hours worked. And now in the command line on the left, I'm adding margins plot, which now automatically visualizes this in a nice way. That's what we get. So we have the usual hours worked on the x-axis, and then the outcome would be my wage log transformed. And of course, what we could now improve is the labels, the titles, the visualization as such. There are a few tweaks we can do, and that's exactly what we're going to do now. Here are the options. For example, instead of using these bars for the confidence intervals that you see here, I'm going to use areas, which looks a little nicer. I'm also going to add more meaningful titles, especially for the y-axis, to overall help me interpret this result a little better. So let me rerun this command, the margins plots plus the options. And now that's a little easier to look at. So we have the hours worked per week. That's my X title. And then the predicted log hourly wage. That's my Y-axis. And what we see is that we have a linear positive relationship between hours worked and hourly wage. The more I work, the more I will earn. And that, of course, is a very expectable result. More hours, more wage. What we also see is that the confidence intervals tend to grow larger towards the extremes of the distribution. The reason for this is that typically we have fewer observation at the extreme values of a distribution, which means that we are less certain about the relationship. And there could be situations where, no, these are just statistical noise. And that's why the confidence interval goes up and becomes broader. Whereas where we have a lot of observations, then the confidence intervals will shrink a little. And that's also what you typically see when you run these regressions, that the confidence intervals are different at different levels of your independent variable. Again, I save my results, and then I'm good to proceed with my next chapter. So we've already visualized our first regression result, a simple linear regression where we look at the relationship between hours worked and the wage that I earn as a result. All right, I hope you're eager to dive a little bit more deeply into the topic. Now we're looking at moderations. That's where things become a little bit more interesting. Now for this part, we need to introduce a moderator. A moderator essentially, in theoretical terms, is a boundary condition, a condition under which the main effect between hours worked and my wage is either strengthened or weakened. Typically, we use these moderation hypotheses to test underlying mechanisms. That's what we look for in a theoretical argument, that the boundary condition, our moderator, strengthens the underlying mechanism between the hours worked and the predicted log hourly wage. In my case, I think a good moderator could be age. If I'm older, maybe that relationship will be tilted upwards because I have more experience, I have a stronger status in my organization, and that will mean that even if I work fewer hours, I will still earn higher wages compared to a junior. And that may resonate with your experience. If you're, for example, a trainee, then even if you work 40 hours, you will still earn a lot less than a senior who is 20 years older than you are. And that is what we're now testing, if that experience effect or now that tenure effect matters. So I'm using age here as my moderator. First thing, I'm running my regression again. In this case, the two hashtags here indicate to Stata that I want to compute the interaction effects between hours and age. And that is exactly what, statistically speaking, a moderation is all about. We are interacting, that is multiplying hours with age. Then in our regression, we will see that we have the direct effect of hours and age plus the interaction effect of hours times wage. The C dot in front of the variables indicates that both these variables are continuous variables. Remember, we had the I dot married. That indicates a binary variable. In this way, Stata knows, okay, for this moderation, we're not looking at a binary variable, we are looking at a continuous variable. That just makes sure that the prediction is accurately computed. One note in terms of interpretation, when I look at these regression outputs and they feature an interaction term here, this hours times wage, it's usually not a good idea to interpret the direct effects. Reason is simple, because now hours basically is featured twice in the model. We have the direct effect of hours, and then hours appears again as an interaction. And the same is true for age. Age appears as a direct effect and as an interaction. As a result, we could end up with a multicollinearity problem, meaning that the two effects may cancel each other out. Hence, if I want to only interpret the direct effect of hours and wage, I should run a separate regression without the interaction term. So I could do that. I just delete those, then run the regression again with hours and wage. So I can add those manually here, run the regression, and then I see also that the results change. For example, age is no longer significant where it was significant in my earlier regression. That's something to note. We're going to go back to our interaction because that's what we're primarily interested in. As before, we save our moderator range in a local. To do so, we first summarize age. It runs from 34 years to 46 years. And then I store the mean, the standard deviations, and one standard deviation above and below the mean value. These are typical cutoff points for moderations. When I look at a moderation, typically I want to look at whether the main relationship between hours worked and wage will shift as a function of age. Therefore, I need to compute different levels of age: low age, middle age, high age. That's what I'm doing here. The mean is middle, so I'm taking the average essentially, which is around 39. And then I'm using a 1 standard deviation more above and below the mean value. In this case, it's 3 years above and below the mean value. That's what I'm using here. And I'm saving those values, in this case, 36, 39, and 42 in my locals so that I can use those to run my margins plots. In this case, we see that these are now saved as locals, and I can also compute my margins. In this case, I'm computing the margins at different values of the hours worked. In this case, going from the minimum to the maximum. And for late age, I have 3 categories: low age, mean age, and high age. And again, I can use the margins plot to create a visualization, which then looks like this. Oh, a little ugly. You know, it's really hard to see anything here in this plot. Especially here, the confidence intervals, they overlap strongly, making it really hard to see. That's why in my options here, I specify no CI, which means no confidence intervals. And I'm also using black and white color scheme here, and also different styles, for example, short dash, dash, and solid, to make it easier for me to visualize the differences. As before, I'm also adding a legend. I'm adding graph specifications, proper X titles and Y titles, so that overall my visualization looks a little bit more beautiful. So now, sorry, I'm going to run all these again. Okay, now it's correct, as it should look like. So one of the locals wasn't saved properly. That's why we had this odd-looking result. But what we see now is whether the hours wage or the hours worked is affected, or the effect strength is shaped by the age of the individuals in our data set. We see that the line, the solid line, is flatter. That is, for older people, the relationship between hours worked and wage is weaker than for younger people. So younger people, when they work more, they tend to get a higher wage increase compared to older employees. That is the first step towards understanding these interaction effects, but that's not the whole story. What we also want to understand is whether these differences are also statistically significant, whether these are different from each other. Now, you could, for example, in this plot, see that at around 30 hours per week, there is no difference really between these 3 types. Now, they intersect here in the middle. There's no difference, but at higher and lower values of hours worked, there seems to be a stronger difference. And that's essentially what we're trying to test now. When and where are these differences statistically significant? And that will be our part 2 of the moderation analysis. Understanding in which range of age is that moderation statistically significant? In other words, where is that moderation statistically significant from 0 or different from 0? All right, lots of annotations again, but the basic logic is the same as before. Stata has still stored my regression results. So the regression that I ran in my earlier command here, that is still in Stata's memory. Everything that I need to add now, again, is my locals. I summarize age, but this time I'm not going to use the mean value and the standard deviations above and below the mean value, but instead I'm adding percentile values. If I use the detail option after summarize, I get the percentile values of age. For example, the first percentile is 34 years of age, the 5th percentile is 35, and so on, and the 99th percentile is 45 years of age. Those values that I see in my output window now, they are then saved as locals. I use the names P5, P25, P50, etc. to name those values, and they are now in Stata's memory. In addition, I'm also specifying the range of age for which I'm trying to plot this. And now I'm going to jump a little bit in my script to the bottom, where I again run my margins command. After having stored these values that you see in the output window, I'm using the margins command and look at the marginal effect, the first derivative of my regression function, at the values, at the percentile values that I saved earlier. The only thing that is really different from my earlier margins command is that I'm adding this dx, dy dx hours. So I'm looking at the margins as a function of the hours work. And that's how we get to the actual test of the moderation. So when we take the first derivative with respect to the hours worked, that is where I actually start testing the statistical significance of my marginal effects. The rest of the visualization is the same as before. I again use the margins plot. The only thing that I really changed compared to my earlier visualization is that I added this dy dx option and that I used a different range for my age, so that I not only have 3 values for age, below the mean, mean, and above the mean, but I have a fuller range of age, and that helps me understand where exactly that becomes significant. Enough explanation, let's look at what that looks like. Remember, I have stored my regression results still in status memory. I don't need to rerun it again. The only thing that I need to rerun, essentially, because I stopped here, is to put the locals into status memory, and then I can directly jump to the marginal effects. In this case, I added the option quietly, which suppresses the output. We don't really need it. And then we can look at the margins plot. This is what it looks like. In terms of interpretation, it tells me where, in terms of the percentiles of age, the moderator, in this case age, is different from 0. We have the 0 line here. This is the gray dotted or dashed line. And everything that is far away from the 0 line means that it is significantly different from 0. In this case, the effect is statistically significant. What we see, okay, for low age, 5th percentile, 25th percentile, 50th percentile, 75th percentile, the curve is far above the 0 line, and also the confidence intervals don't overlap with the 0 line, which gives me a strong indication that here the effect is actually significant. The only thing where things become a little murky is at very high levels of age. So the 95th percentile, I think that was like 45 years of age. That's where the differences no longer is statistically significant, at least seemingly here. If we want to be 100% sure about this, we can also compute this difference. And that's where the code becomes a little tricky, I must admit. I'm not only going to give you the high-level logic and leave it for you to look at this after the seminar. So essentially what I want to do is I want to compute the marginal effect of hours at every integer of age value and compare each adjacent peer. So in other words, I want to look at the question, or I ask, is the slope at age 30 different from the slope at age 31? No, and in this case, we look at percentile values. Is that really different? That's what I'm doing with the PW compare, the P pairwise compare option in Stata. We have the same margins command as before, but now we're also comparing whether any pairs are statistically different from each other. Next, I'm going to save these results in a matrix, and those results are then converted into vertical lines that indicate where the cutoff point is for statistical significance. There's a lot of code for essentially one line, as you will see, that shows where the cutoff point is. But what I want to see is at which point in this figure that you see right now on the screen is the cutoff point where the results are statistically significant. I think it's easiest if we just run the whole command and look at the results. Running this again, and you see the only difference is a gray vertical line at the 75th percentile. This line indicates that at this point, the result is still statistically significant, so the difference is still statistically significant, but after this percentile value, the results turn insignificant. That's what I'm adding here for my moderation. And that's a nice twist that you can add. It's completely optional. You don't have to do it. Also, in this case, just looking at the confidence intervals gives you a good sense of where the results are significant. But if you want to add it and be like 100% sure, you can do this extra computation and add that to your output results. And again, I save the results and I'm essentially done. What we've now covered is how can I test a moderation analysis in Stata for a linear regression where I have a linear predictor and a linear outcome model. And we have now seen two different ways in which we can visualize these results and also test where this result is statistically significant. Are we ready for more? I have a little bit more to share on nonlinear models. Nonlinear models essentially just means that your dependent variable is not continuous, but for example, binary. And that will then help me understand a few things, or maybe I should start this way. The difference between a linear and a nonlinear model is that the coefficients are not so easy to interpret. In a linear regression model, a 1 unit increase in my independent variable, for example, a 1 unit increase in the hours worked per week, leads to a coefficient size increase or change in my dependent variable. If I look at my regressions earlier on, let me just run back to this earlier regression. If I look at this result, then 1 hour more in work results on average in a roughly 7% increase in my wage. That is now the rough interpretation. And in this case, I say the percentage because my dependent variable is log transformed. Otherwise, it would be a unit increase. If it were not transformed into a log transformation, it would be just the number of dollars I would get more for each hour worked. So for example, if I just add wage, then 1 hour more in work results in the coefficient size increase in my wage. So this would be probably what, 5 to 6 cents, I guess, if that's the unit. That will be the typical interpretation. If I go to a logit regression down here, then the relationship between the dependent and independent variable is less straightforward because we don't have a linear prediction model, but we have essentially an S-curve in a logit model. And the slope of this S-curve is, of course, different at every point estimate. I also have a YouTube video on this. If you want to learn more about this, check out my website. You'll find all the videos there and can look at logit regressions in more detail. Now, I'm going to run this logit regression. And again, it includes an interaction term. We already know that the two hashtags here indicate that I want to interact, that is multiply two variables. In this case, grade is the number of school years, and then race is the categorical variable that we had earlier. It had white, black, and other. And the C dot means that we have for grade a continuous variable, and for race we have a categorical variable. It is not continuous, and that's here particularly important, so that Stata does not treat race as a continuous variable. It has 1, 2, 3, but this is not a continuous variable. It doesn't mean 1 is higher, lower than 2, or 2 is or 3 is higher than 2. It is distinct categories, and that's what I need to indicate here. So very important to not forget the I dot. The rest is very similar to what we had before. First of all, I store the cutoff points for my moderator in my local, so my memory, or my independent variable as well. This case for grade, it's a continuous variable where I store the maximum and the minimum grade in my local, and then I can compute the margins for the minimum to the maximum grade with intervals of 1. And I also want to look at whether those margins, whether the relationship between my schooling and the wages, and the type of job that I'm earning, whether I'm, the type of job that I'm taking, whether it's a blue or white collar job, changes as a function of race. Let's take a look at the results. Then these things become a little clearer. I now computed my margins again. And as before, I have my margins plot with a few options, labels, titles, beautification. Oh, sorry, I need to run the whole thing. Otherwise, part of what is stored is not in the memory. And here I now have my output for a non-linear regression results. As you see, now this is not a linear prediction anymore, but we have a kind of a curve. And that is what you would typically see if you have a nonlinear results or nonlinear regression model, that the results and the visualization is also kind of a different type of shape because the margins are different at every slope point. What I see in terms of interpretation, that the relationship between schooling and the likelihood of having a blue collar job decreases. So the more years of schooling I have, the less likely I am to have a blue collar job, which probably also resonates with our intuition. Now, if I have a lot of education, I may be more likely to work in professional services. And if I work in manufacturing, maybe I go on a traineeship earlier, I have less years of schooling. We also see that this relationship is different depending on the race. So for white, the decline is earlier and stronger than for black and other, for example, here. The question that we now want to answer is whether these differences that we see here in the three slopes is also statistically significant. What I need to do in order to assess this is we need to compare it against the null hypothesis. We do the same trick as before, that for the margins, we are adding the dy dx with respect to our key variable. That's what we're going to do at the bottom here. The only thing that I'm adding is that I'm computing the margins with respect to grade. That's the only thing I'm really adding here. Everything else remains unchanged, but the resulting figure will be quite different, as you will see in a minute. So let's run this again. I need to run the whole thing again so that everything that's stored in my locals is accessible once I go to the margins command here. So I have access to the grade min and the grade max, which are stored in locals further up in my code. No, so remember, they are stored here. Always remember, if you have locals, you need to run the whole thing where the locals are created in one go so that you can get access to all the values in the margins computation. And again, I added the quietly command because otherwise I will get a very, very long table, which at this point I don't really need. Only Stata needs it to actually compute the relevant values for my margins plot. But for me, in terms of interpretation, at this point, it is less relevant because I'm mainly interested in that visualization. Let's take a look at this. So let's, oh, sorry, I need to run it again because it calls on the locals again. Let me run the whole thing. And then I get this visualization. In this case, I'm also seeing where the effect of these three different groups is statistically different from 0. Visually, I already can see that the lines for few years of schooling are very close to each other, and they are also overlapping in terms of confidence intervals, which already gives me an indication that here for very few years of schooling, like if you only have primary school, now then there's no real difference in the likelihood of having a blue or a white collar profession. However, as the schooling increases in years, we see that the difference becomes stronger, and that we also see that there are stronger differences between the three groups that we have in our data set. And as we move towards higher numbers of schooling years, that's where the differences become lower again. Perhaps what I might be interested in as well here is where exactly is this cutoff point? Earlier, when we looked at our linear regression model and the moderating effect of age, it was relatively clear where that cutoff point was, visually speaking. In this case, perhaps I'm a little less certain, and that's where my vertical lines that indicate where the cutoff points are may matter. What I'm going to add now are two lines, one for the start of where these differences become statistically different from zero, and where the end of that significance area is. Because as you see now, there seems to be a middle range where the values are significant. Again, I have these optional steps 4 to 6 and 7, where I do this. It's the same logic as before, that I do the formal pairwise test with the PW compare, the pairwise compare test in Stata, which is a simple option in the margins command that allows me to actually test these differences and then compare them. And as before, I'm going to store those values in my memory, in Stata's memory, so that I can call them, and then I can directly compare whether the differences are different across my categories. That's what's happening here. So for each of the categories, I'm computing the margins. For example, if race is 3 or 2 or 1, and do the PW compare command. All of these are then stored in Stata's memory, and I can then compute the cutoff points where these effects are statistically significant. That's what's happening here. And then I'm using those computed values to create those vertical lines where these differences move from being insignificant to significant. So again, a lot of code. Probably it's easier if you walk through this on your own with the annotations. But the basic logic is we want to create those vertical lines where the cutoff points are statistically significant. Let's take a quick look at what this looks like in practice. I run my regression results. I compute all my locals. And then in the end, I also have my second moderation plot, the margins plot. So that's the first one. And now comes the second one, which now adds those vertical lines. In this case, the dashed lines, the vertical dashed lines here, the red, is where the effect starts to be statistically significant. So for the red, that's where the cutoff point is, where it starts becoming statistically significant. So this range from year 4 all the way till year 17, that's where the red line is statistically significant. So in that range, for the group black, that's where the difference is between years of schooling and the likelihood of becoming a blue collar worker is statistically significant. So we see the effect is negative. So in that range, it kind of increases the likelihood of having a white collar job, or decreases the likelihood of having a blue collar job in that range. But below and above that range, it is not statistically significant. And for the group other, for example, we have a green line, a vertical green line. The dotted green line is where the significance starts. That's at age 12. So you see with the confidence intervals, they just about touch the vertical, the horizontal 0 line. That's why this is probably not yet significant, but at year 12, that's when the significance starts, and it goes to school year 14. That's again when also the confidence interval overlaps with the respective horizontal null line against which I'm testing this statistical significance. So in this way, you can not only test where in which range your moderation becomes statistically significant, but you can also visualize it and show it to your reader, to your audience, where exactly do these differences matter. For the blue line, the confidence intervals are very narrow, and I told Stata, well, if the whole range is statistically significant, then you don't need to add any lines, and that's exactly what's happening. So for the white group, the whole range is statistically significant, and it's also a very narrow confidence band. And that's why there's no line for the white group. No blue line is present here, just because now the whole range is covered. We have now the final line of code, which is to save this figure along with my other figures in my document folder. Now I've saved everything. I've my direct effects, I have my descriptive statistics, I have computed my moderation analyses. I've tested where in which range these moderation effects are statistically significant, and basically I'm good to go. Now I've done all my analyses. I can write it up and present it. So well done. Thank you very much. That was it. If you have any questions, feel free to ask questions. If there are any clarifications needed, very happy to talk about these things. And again, I invite you to check out my YouTube channel. There's a lot more also on U-shaped tests, for example, how you can do this, or if you want to work with panel data, lots to discover. You're warmly welcome to check out the YouTube channel Statistics Made Easy. Thank you.